Good evening, our students, and welcome to this moment's class. We have just had a class on the introductory aspect of chi-square goodness of fit tests. So we refer you to the class if you have not had the opportunity of viewing the class. This is just a way of taking real life examples and solving under chi-square goodness of fit tests. The question here says, John is testing an octahedral die. That is a die that contains 8 faces. To see if it is biased, the results are given below. First of all, for you to confirm if a die is biased or not, that die has to be flipped several times. And then you record each time each particular face comes up. If it is unbiased, it implies that the number of the times that each faces are going to come will be very close, if not equal to each other. Otherwise, it is unbiased. What did John do? John decided to flip this die 80 times and recorded each time that the first face down to the 80th face came up. And then the first face came up 7 times, the second one 10 times, down to the last one that came up 7 times. So the concern is, using this record of John, how do we determine that the octahedral die, is either biased or not? And what is the best statistical tool that can be applied to confirm this question or to answer this question? Our previous class, which I said, is the introductory aspect on the chi-square goodness of fit tests. Already explained that when we want to determine if a set of data is coming from a specified distribution, that we should be making use of what we call chi-square goodness of fit tests. What is this kind of a question trying to ascertain? If the octahedral die is uniform. Uniform in the sense that each face has the same probability or chance of occurring. That is what we call fair. That is what we call unbiased. But if the faces have different probabilities of coming up now, we say that it is unbiased, we say that it is biased or that it is unfair. And of course, you know in statistics that a distribution where each of the faces have equal probability of coming up is what we call uniform distribution. So by implication, we want to determine if this octahedral die is uniform, making use of this data set. In that previous class, of course, we already had a kind of stated all the steps that one should follow when one is conducting chi-square goodness of fit test, beginning from stating the hypothesis. So as a way of providing the solution to this question, we were asked to test the hypothesis that the die is fair at alpha of 0.05. So we have here as a solution. We begin by stating the hypothesis. We say H subscript 0, which we call the null hypothesis. The die is fair. Against the alternative H subscript 1 that says that the die is not fair. Then the level of significance we are going to use here is 0.05. Then we are going to recall for ourselves that each time we are confronted with chi-square tests, that we should first of all obtain the expected frequencies from the observed frequencies. And going by the nature of the question we have here, we are talking about something that has to do with uniform distribution. So if this octahedral die must be what? Be uniform. It implies that the expected frequency in the first phase down to the last phase must be what? Must be equal. And of course, the expected what frequency here is going to be the mean of all these observed frequencies. That is what I said here. Note that here, the expected frequencies are based on a uniform distribution, which gives each expected frequency as sum of all these observed frequencies divided by the number of what? Of the classes. There are 80 classes here. So that gave this to be what? To be 10. That is summing all the frequencies, arriving at 80, and dividing by what? By the number of the classes, which is 8, should give us 10. Then we now come here. We are to use this formula that says that chi-square cal is given as sum over I of O subscript I, talking about ith observed frequency minus the ith expected frequency, all raised to power 2 divided by the ith expected frequency. So for us now to calculate this or to evaluate this, we must first of all record our observed frequencies and equally record our what? Expected frequencies. Take the difference of observed and expected, square it and divide by what? By the expected frequencies. And lucky enough, we have been given the observed frequencies, which is what I have here. These are the scores of the phases of the octahedral die, beginning from 1 and ending at what? At 8. These are the observed frequencies of the number of the times that each phase came up. Of course, we earlier had explained about the expected frequency. So that's why you see that the expected frequency from here down to the last one is what? Is 8. Is the same thing, 10, 10, 10. Because if this octahedral die must be filled, the expected frequency of the number of the times that each phase came up must be what? Must be the same thing, which is what? Is 10. And then you have here to be 10, and here to 10 down the what? The line. Taking the differences here means expected, observed minus expected. Observed here, expected is here. 7 minus 10 will give us minus 3. 10 minus 10 will give us 0. Down to the last one, where we had 7 minus 10 to give us minus 3. Looking at this formula, of course, we square it and then divide by what? By the expected frequency. So squaring and dividing by the expected frequency will give this one to be what? 0.8. That is to say, minus 3 squared divided by 10 will give us what? This value here. Okay? The same thing applies to this place, down to the what? To the last one. Okay? So you can then confirm the values which we have here. This will give me, this will give me 0.9. Because minus 3 squared will give me 9, divided by 10 will give me 0.9. So if you sum all these values here, you arrive at 4.0. Then we now know that our chi-square cal is given as what? As a 4.0. We have now to go and get the value of our chi-square tabulated. And that one requires that we go to what? To table. And we are going to go to table. Before we go to table, we determine the degrees of what? Of freedom. The degree of freedom is simply the number of the classes minus 1, which is k minus 1. We already had explained this thing on the introductory aspect of chi-square goodness of fit test. So you can make reference to that video. So the number of the classes we have here is what? Is 8. 8 minus 1 will give us what? 7. And then the level of significance we have here is 0.05. So chi-square of 0.05, 8 minus 1 is what? Is 7. From the chi-square table, is going to give you 14.067. And we can only reject this null hypothesis that says that the octahedral die is fake if and only if the chi-square calculated is greater than the chi-square tabulated. And of course, our chi-square calculated is 4.0, while our chi-square tabulated at 0.05 level of significance is 14.067. So comparing these two quantities, we come to a conclusion that this quantity is less than this particular quantity. And because of this, we don't have enough evidence from this data set to reject our null hypothesis that says that the octahedral die is fake. So what is our conclusion? Our conclusion is that making use of the available information contained in this data sets, that the information is not sufficient enough to make us to reject the null hypothesis that says that the octahedral die is fake. And therefore, we conclude that the octahedral die is fake. It is what? Unbiased. It is not biased. It is what? Unbiased. Otherwise, we could have said that our octahedral die is biased. We still have a lot of questions that we should be bringing up and be discussing with you on chi-square goodness of fit tests. Remember, on our YouTube, the introductory class on the chi-square test will be tagged Introduction to Chi-square Tests. While this particular class we are making now will be tagged on our YouTube channel, Chi-square goodness of fit test 1. Thank you very much for staying tuned, and then stay tuned again for the chi-square goodness of fit test 2, 3 down the line. Thank you for your audience, and see you in our next class.